All right, and we're back at 9.3b. We're going to look at something called the ratio test, which is going to be our last test. It doesn't mean that that is the end of all possible tests for series convergence and divergence, but this is the last one we're going to look at in this class is the ratio test. And then we'll have a little summary of all the tests here at the end. All right, so, and it does tell us if things converge absolutely, besides just telling it about if they converge, but also converges absolutely. So it's cool that it gives us that extra bit there. So what we do is we look at the ratio. That's why it's called the ratio test. The ratio of the n plus 1 term and the n term in absolute value. And then we take the limit as it goes to infinity. And if that limit is less than 1, that means it converges absolutely. So like if it comes out to like 0.9, it converges absolutely. Comes out to 0, which is often the case, converges absolutely. All right, but if it comes out to something bigger than 1, so if we're greater than 1, then it's going to diverge. So this actually does tell us pretty quickly if it converges or diverges, and it tells us if it converges absolutely or not. All right, but if it equals 1, then we have a problem. It's inconclusive. It doesn't tell us if it converges or diverges, so we've got to do some other test. All right, and it is really helpful when we're working with factorials and exponential functions particularly. All right, so let's do a couple of ratio tests here. So if I look at this guy now, it's exponential on the top, it's factorial on the bottom. I don't know which one of those is bigger, so I can't even do like the limit as n goes to infinity to do the nth term test because I don't know what's going to happen. But I can do a ratio test. So if I do a ratio test, we'll take the limit as n goes to infinity. So I plug in n plus 1 here, so I get 2 to the n plus 1 over n plus 1 factorial. And that's all over just the regular guy, 2 to the n over n factorial. And all of that's an absolute value. So what ends up happening with these fractions is we always just flip and multiply. So later on, I'm probably just going to skip straight to the flip and multiply part. But we've got 2 to the n plus 1 over n plus 1 factorial. And if we flip this guy over, we get n factorial on the top and 2 to the n on the bottom. We don't necessarily need the absolute value bars anymore. There was no negative terms in here at all. So now we can just try and cancel out stuff. So this 2 to the n is going to cancel out with this 2 to the n. And it's going to leave us with just 1, 2 on top. Right? There was one more of them on top. With the n factorials, so n plus 1 factorial means n plus 1 times n minus 1. So we could write that as n plus 1 times n factorial. And then those are going to cancel out. So what we're left with is 2 over n plus 1. Now if we go back and take the limit as n goes to infinity, this goes to 0. So now that we know that this goes to 0, which is definitely less than 1, that this guy converges. And he doesn't just converge, he converges absolutely. Not like it mattered here because there was no negative sign, but this guy definitely converges. All right, so that wasn't too hard, I hope. Let's take a look at the next one here. All right, so we've got 2 to the n plus 1, 3 to the n. So we got 2 to the n and 3 to the n. It's kind of geometric, but there's this other n squared in here. Gosh, who knows what's going on there. So let's do our ratio test. Limit as n goes to infinity of this guy with n plus 1 plugged in. So if we plug in n plus 1, we're going to have n plus 2 here over 3 to the n plus 1. And this would be all over the regular term, so we just flip and multiply. So 3 to the n, n squared, 2 to the n plus 1. Technically, this is all an absolute value, but we don't have any negative signs in here, so we should be okay there. So now we just kind of cancel out some stuff. So the 3 to the n cancels completely and leaves us with a 3 down here. The 2 to the n plus 2 and 2 to the n plus 1, the n plus 1 is going to cancel completely and leave us with 1, 2 up there. And we've got some n squareds left. So this is 2 times n plus 1 squared over 3 times n squared. All right, so we could kind of put these together if we wanted to. All right, but either way, if we divide this right here, which we can do, we'd get, and again, we don't necessarily have to do this, but 1 plus 1 over n squared like that. And now if we take the limit as n goes to infinity, this guy is 0, or this guy is really just 1 squared, so it's 1. This guy here is 0, and we get 2/3. All right, you could have said here, we'd be like, oh, n squared on top, I got an n squared on the bottom. It's also going to be 1 right there, but, you know, we still got the 2/3, so 2/3, which is less than 1, so that means it converges. Technically, it converges absolutely, but converges. This guy, he's good. This one, He's good. How about this one? All right, so we found out in the first one that n factorial was bigger than 2 to the n. Like this guy got really small. Eventually, the whole term got really small because the bottom, I guess, got bigger much faster. But now, instead of 2 to the n, what about n to the n? Because that gets even bigger. So let's look at this guy using the ratio test. All right, so we're going to have n plus 1 to the n plus 1 over n plus 1 factorial. And then we're really dividing by this guy, so we just flip and multiply. N factorial over n to the n. All right, well, what happens here? So n plus 1 and n factorial. I guess I should technically have some absolute values. So this is n plus 1 times n factorial. So the n factorials cancel, and I just get an n plus 1 here. Well, one of these n plus 1s could cancel out with one of those n plus 1s. All right, this is n plus 1 to the n plus 1. So we get n plus 1 to the n over n to the n. Or we could say this is n plus 1 over n to the n, which is, doing the division here, 1 plus 1 over n to the n, the limit as n goes to infinity. Now you got to think back, way back to limits. What is this limit equal to? All right, well, this was actually a definition here. So 1 plus 1 over n. So it's really like 1 plus 0 raised to the infinity. But this isn't quite 0. It's just really close to it. And what this ends up working out to is e, which is bigger than 1. All right, so that means if we're bigger than 1, that means it diverges. All right, bigger than 1, diverges. So this guy, this n to the n, does get bigger than n factorial. All right, so that's all of our tests. So now we're going to go through some strategies. So when you're doing these, usually the first thing I want to do is just ask, does the limit go to 0? If not, then it diverges. If it does, we go on down to the next step. Think of this kind of as a flow chart. Next, is it a geometric series? If r is less than 1, it converges. If r is greater than 1, it diverges. Most of them won't be geometric, though. Is it a p series? P series is cool, nice and easy. If p is greater than 1, it converges. If p is less than or equal to 1, it diverges. And if it's not any of those three things, the three, what I like to call the easy test, then we can do the ratio test, the integral test, or a comparison test, which could be the limit comparison or direct comparison, or the alternating series test. All right, so we've got 3 examples here and 3 examples on the next slide, and that is it for convergence, I believe. So this guy, I've got n plus 1 over 3n plus 1. If I just look at the limit as n goes to infinity here, and hopefully this is something you can see before even having to write it out, just in your head, that this is going to go to 1/3, which is not 0. Therefore, this diverges by the nth term test. Remember, it has to go to 0 at the end. Otherwise, you keep adding 1/3, and it's going to keep getting bigger. All right, let's see. This guy, the limit here would go to 0 because the top's smaller than the bottom. Is it geometric? It most certainly is. All right, our r is pi over 6, which is definitely less than 1. Therefore, it converges. All right, next one. Oh, gosh. All right, so this is really n over e to the n squared, like that. All right, does the limit go to 0? Yeah, the limit is going to go to 0 here because the bottom's an exponential much bigger than n. It's definitely not geometric because we're raised to the n squared and we have an n on top. It's not a p series because we need to remember for p series it needs to be 1 over n to the p, like that. So now we can either do a ratio, an integral, a comparison test, or an alternating series test. Well, it's not alternating, that's for sure. We could try and do some sort of comparison, but I'm not quite sure what we would compare it to. It looks like an integral test would actually work if we said u was this n squared up here, but that's often kind of long to do. I usually go to ratio test after this. That's usually my go-to. It won't always work, but it often does. Right? So if we want to do a ratio, well, I'm torn between the integral test and ratio test because both of them would get us our answer, I think. So for integral test, we need to say that it's continuous and decreasing, and that's a little bit of work. So I might just try and go with ratio. So we take the limit as n goes to infinity of n plus 1 over e to the n plus 1 squared times e to the n squared over n like that. And we'll see, does that get us anything? All right, so n plus 1 over n, that's basically going to be 1. E to the n squared over e to the n plus 1 squared. I don't know if that's going to actually give us anything. Well, that actually that should. So this is going to be e to the n squared plus 2n plus 1. So that means e to the n squareds would cancel, right? Because this would be e to the n squared times e to the 2n times e to the first. And that would cancel completely. And this is 1. So we get all this extra stuff on the bottom. So that limit's going to go to 0 because of this e to the 2n on the bottom here. All right, which tells us that this converges. All right, we could have also done the integral test. And if we want to do the integral test, let's just take a quick look here. If we look at the integral of n over e to the n squared dn, our u would be this exponent. Our du would be 2n dn. So, and again, we're going from 1 to infinity here. Don't forget the bounds. So we need a 2 and a 1/2. So we get 1/2 e to the negative u du. So it'd be 1/2 e to the negative u over negative 1 or times negative 1. There we go. Maybe I should have just used the negative in the beginning, but oh well, that works. And let's see, this would be negative 1/2 e to the negative n squared from 1 to infinity. We plug in infinity, we're getting 0. We plug in 1, we're getting a number. So this equals a number. So that tells us that it should converge as long as it's decreasing, and continuous. All right. So that would also tell us it converges. All right. Just wanted to throw the integral test in there once. All right, 3 more examples. So 1 over 3n plus 1. So the limit does go to 0. It's not geometric. It's not quite a p-series. It looks pretty close to the p-series. It looks like it's almost 1 over 3 to the n, or 1/3 times 1 over n, like that. And it's actually always going to be a little bit smaller than that, but let's do the limit comparison test then, because I can compare it to this guy and it should do the same thing, or I can compare it to just that guy. So if we do the limit comparison test, we get 1 over 3 to the n plus 1 over 1 over n, and we take the limit as n goes to infinity. All right, and this is just going to be 1 over 3 to the n plus 1 times n over 1, or n over 3 to the n plus 1, which gives us 1/3. If we take the limit, we're just looking at that. All right, so that means this guy will do the same thing that this guy does. All right, this guy diverges, so that means this guy also diverges. All right, he's very similar to just 1 over n, is what we're basically saying here. All right, next up, we've got a -1 in here. All right, so -1 in there tells me I'm probably going to do the alternating series. All right, so if we look at one thing, the limit as n goes to infinity of 3 over 4n plus 1, that goes to 0. That's good. The next thing, is it decreasing? 3 over 4n plus 1, is that going to be greater than 3 over 4n plus 1 plus 1? Well, that'd be 3 over 4n plus 5. So yeah, this bottom's bigger than this bottom, but the tops are still the same. So this does check out too. Both of them work, so that means it converges by the alternating series test. And finally, this guy, n factorial over 10 to the n. So it's got factorials and exponentials. So it's definitely, I'm not sure about the limit. It's not geometric. It's not a p-series. We probably want to go straight to ratio test on this guy here. So if we do the ratio test, the limit as n goes to infinity of this guy with n plus 1. There's my plus sign. And divided by this guy, so we'll flip it and multiply. Lots of stuff is going to cancel out here. Like the 10 to the n is going to cancel completely and leave us with just a 10 on the bottom. The n plus 1 factorial and the n factorial are going to cancel and just leave us with n plus 1 on the top. So we get n plus 1 over 10. And we're taking the limit as n goes to infinity. That goes to infinity. All right, so that's definitely bigger than 1. That tells us that this diverges. All right, so n factorial is bigger than 10 to the n. All right, so here's a summary now of our test. So we've got the nth term test. We just look at the limit. It tells us if something diverges only. All right, cannot be shown to test convergence. We've got the geometric series. If r is less than 1, it converges. If r is greater than or equal to 1, it diverges. And we even have the formula for the sum. That's really the only one we have a formula for the sum for. All right, the p series, it's a very special case, 1 over n to the p. If p is greater than 1, it converges. If p is less than, p is greater than 1, it converges. If p is less than or equal to 1, it diverges, like 1 over the square root of n. All right, alternating series, we need that it's decreasing, and we need that the limit goes to 0, and then it will converge. Otherwise, it diverges if those aren't met, and we can find the remainder of the sum there. We've got the integral test, but we need that it's continuous, positive, and decreasing. I didn't forget to check positive before, but that's usually pretty much a given. We look at the integral. If the integral gives us a number, it converges. If the integral diverges, then the series diverges as well. The ratio test, that's a fun one. Like we look at the limit of the terms, the n plus 1 term over the n term. If it's less than 1, it converges. If it's greater than 1, it diverges. If it equals 1, it's inconclusive. The direct comparison test, all right, so if it's smaller than something that converges, then it also converges. If it's bigger than something that diverges, then it also diverges. And the limit comparison test is we just take the limit of those two series, or their general term. If it equals a number, then they either both converge or both diverge. All right, so that is a summary of all of our tests for convergence, and that is it for 9.3, so go check on the homework online.